Okay, so the last thing I'm going to talk about, we'll get through things kind of quick here today, is Kirchoff's law. All right, so Kirchoff's law is basically this statement that absorptivity, alpha, at a given wavelength, at a given direction, theta and phi, is equal to emissivity at that same wavelength and direction. So a very simple law, but it's really kind of remarkable, right? Like it's not obvious that a property would absorb exactly the same rate that it emits, right? This is true for real surfaces, for black body surfaces, right? For any surface, this is always true. So yeah, this is also for real surfaces. But again, like, why is this true? Well, it's because if you look back at that spectral map that we showed, there's only certain energy states that are available for emitting. It's the same mechanism for emitting as it is for absorbing, right? The electron changes shell, or there's a vibration in the phonon, or whatever, right? There's the same mechanisms exist, so this is sort of a true law. We can again extend this like the same way we did with other things, so we can say for diffuse. For a diffuse surface, we can say alpha lambda is equal to epsilon lambda. And we could say for diffuse gray, alpha equals epsilon. Okay? Oftentimes, when you're actually modeling a system, and you know that maybe there's some wavelength dependence on your properties, you might just simplify the equation and say, okay, I have like we'll call it a diffuse gray surface, but if I integrate it over the entire thing and I make some sort of simplification, you might say that alpha is one value and epsilon's another value, or you might separate those out and just model them differently. But just keep in mind that like the underlying physics of the problem say that can't actually really be true, right? But you sometimes simplify it that way. One example is like in solar applications. Let's say like you're absorbing light from the sun, and you absorb at a really high temperature, because the sun's at a really high temperature. You're absorbing the light coming from that high temperature, but you're emitting at a much, much lower temperature. So you might look at the absorptivity in the solar region, and then the emissivity of that surface in the thermal region, and have two different values, but be able to model it pretty well with a uniform value. Okay. So let's maybe look at one example I have here. This is kind of ties some things together. So what we're showing here is the solar radiation spectrum. So let's zoom in here. So if you were to go out and sort of measure as a function of wavelength the intensity of light that's coming from the sun, and you say we're out on a satellite, and you did that, you're outside the Earth's atmosphere, you would see this yellow trace, right? And this sort of gets to the question about can we ever exceed the black body spectrum? Well, the sun spectrum shows that you actually can, but if you look down and sort of drill down into why that is, it's because of these band gaps in emission. So we're not like violating the physics here. Okay, but this is the solar spectrum. What we see then if we like take a reading on the surface of the Earth is this red spectrum. So you go from having like pretty much a straight black body distribution down to this distribution with a bunch of gaps in it. So this is what we actually experience, as we're sort of outside on this sunny day. Why is this interesting? Well, I mean, one, it sort of indicates where the radiation is spectrally that's hitting us. But the other thing is, like, if we talk about the greenhouse effect, right, which is of great importance to our survival, right, both in terms of keeping the planet warm enough, but in terms of potentially causing problems for us. We can look at the things that cause the greenhouse effect. So this is sort of the underlying root cause of global warming, is this idea that CO2 absorbs at different wavelengths differently, right? H2O does as well. H2O is a big greenhouse gas, but CO2 is a greenhouse gas, and importantly, it's a greenhouse gas in some areas where H2O is not a greenhouse gas, right? Just because CO2 is in the atmosphere doesn't mean it's absorbing all wavelengths. It's only absorbing certain wavelengths. So what we can do is let's figure out where it is that we care whether CO2 is absorbing. So first of all, let's maybe look at this wavelength. And let's remember that Wien's law says lambda max is equal to this constant 2898 divided by temperature. So let's assume that the surface of the Earth is at like 15 degrees C. So that'd be 15 plus 273.15. So if you do this calculation, you get that the peak, so the lambda max, that is the wavelength at which the intensity of radiation from the surface of the Earth is highest, is about 10 micron. All right. So again, that's the kind of the peak of the black body curve from radiation emitted from the Earth out towards space. All right. So now if I draw on this plot here where the Earth is emitting, it sort of looks like this. Right. So this is where the thermal radiation from the surface of the Earth is. So do we see now why CO2 is a problem? Right. CO2, this particular band down here, this fourth band, is really problematic because it's filling in where H2O is not absorbing, and it's right smack dab in the middle of where the Earth is emitting. Okay, so what does the Earth have to do to respond to this? Like if you put a blanket around something that's generating heat, what is that thing going to do? It has to get hotter to balance things out, right? So what ends up happening is, in order to kind of get around this, let's see if I can do it this way. This whole thing has to shift over, right? So it's shifting over, that means temperature is going up, right? So this is sort of the origin of a lot of engineering problems and issues for humanity, but you guys are all engineers and smart and we'll figure it out, right? So anyways, this is a real practical application related to what we call real surfaces, these spectrally dependent surfaces, spectrally dependent properties. You can see that it's sort of important to real things we care about. So that's all I had for today. Any questions on this before we wrap up? Okay, great. I'll see you on Monday.